problematiche, le alternative che sono state illustrate in un'ottica di sistema, come diceva il professor Consonni, parlando del ruolo che possono avere nell'ambito complessivo della risoluzione del problema legato appunto all'emissione di gas climalteranti e di cambiamenti climatici. Please, Bob.
So to begin, I'd like to thank Stefano Consonni and the organizers of this conference for inviting me back to Politecnico here in Milan. And this is the third time that I've made a presentation in this particular conference room, and I think each time I've been in the same chair. So what I'm going to talk about is something quite different from what others are talking about here. Most of the focus on carbon capture and storage throughout the entire carbon capture and storage community is focused on power generation, but it's going to be also very important to think about this for liquid fuels production. And the title of my talk is Toward Transportation Fuels with Zero Greenhouse Gas Emissions. And if you think about that for a moment, you'll come to the you'll quickly realize that it seems that doing carbon capture and storage for transportation is inherently much more difficult than for large stationary conversion plants, because you can't very easily envision capturing CO2 from the tailpipe emissions of a car, and hauling that off somewhere to put it underground. But what I'm going to show you here is that there are plausible ways to do this, not at the point of end use, but at the point of energy conversion. And the key idea that I want to focus on in my presentation is to think about doing carbon capture and storage for biomass energy conversion, and to do this in conjunction with the co-processing of biomass and coal in systems that make useful energy with carbon capture and storage. So that's the approach that I'm going, but I'm going to give some background to that before I get underway. I did something wrong here. To advance,
This one.
Oh, that one, okay.
Yeah.
To begin, I would like to say that some of the results that I'm going to present here are based on a collaboration involving, at Princeton University, Eric Larson and myself, an American colleague, Haiming Jin, and two of our Politecnico colleagues, Stefano Consonni and Giulia Foresi. And I'm going to put the transportation problem into the context of the wedges strategy that Stefano has already articulated. And as he pointed out, if you want to stabilize atmospheric CO2 at 500 parts per million, you essentially have to keep emissions flat for 50 years. And I'm going to focus on thinking about transportation energy in that same context. In other words, how can we think about evolving a transportation energy system in which the emissions are flat during this half century. And if you begin by looking at the distribution of CO2 emissions, you see that oil and coal each account for about 40% of CO2 emissions from fossil fuel burning. And so if you're going to think about achieving deep reductions in greenhouse gas emissions, you have to think about decarbonizing both power generation, coal power generation, and transportation fuel, which accounts for a large fraction of the total oil use. Now, a point of departure here is the Sustainable Mobility Project Global Transport Energy Scenario that came out in 2004 as a publication of the World Business Council for Sustainable Development. And this is their transportation energy scenario. It goes from 2004, the numbers that I showed in the previous graph here, up to 2050. And you can see there's roughly a doubling of total transportation energy consumption that is expected in this time, and also a doubling of CO2 emissions for transportation energy. So if we want to stabilize transportation emissions, we have to be thinking here about two wedges coming out of transportation between now and mid-century. And you can see in this particular business-as-usual scenario here that there's not a high emphasis on end-use efficiency. For example, in light-duty vehicles, you start out not at the level that Stefano mentioned here, which is 30 miles per gallon, but in here, the starting average fuel use rate for light-duty vehicles worldwide is about 22 miles per gallon, or 8.5 liters per 100 kilometers. And you can see that, 10.4 liters per 100 kilometers. And in this scenario, it only goes down modestly to about 8.5 by the middle of the century. There's also, I'll call your attention to the very high rate of growth for air transport in this area, which is going to be a major contributor to the growth in this period. Well, how do we get these two wedges out of the transportation system? I will show that this is plausibly achievable using near-term commercial technology without significant changes in transport fuel infrastructure and at competitive costs under a carbon policy. And in particular, I'm going to focus on a carbon price of $100 a ton of carbon. And the reason I choose that for the economic analysis that I'm going to present here is because that's the minimum market price needed to induce carbon capture and storage for coal-fired power generation. And if we don't decarbonize coal-fired power generation, we're not going to solve the coal power problem, and we're not going to solve the climate problem. So that's sort of a minimum price on carbon emissions that we need to think about if we're going to stabilize the atmospheric CO2 concentration at, say, 500 parts per million or less. And I'm also going to show that the main impediment to this strategy is not technological, it's not economic. It is probably the constraints are going to be mainly institutional, but they also depend on the viability of CO2 storage at gigascale. In other words, we have to be able to store CO2 underground at rates of gigatons per year, over a large part of this century in order to make this viable. And we don't yet know with a high degree of confidence that we can do that. Geologists and the storage community is guardedly optimistic about this, but we're not going to know for sure until we have supplemented the experimental work that has been done already and a couple of mega-scale projects that have been done at places like Schleipner and Ensala, with perhaps 10 to 12 additional mega-scale storage projects in a wide variety of geological formations in various places around the world. And there's an urgency to do this and to get it done over the next decade. And we ought to expect that in the time frame 2015 to 2020, if we do this, we'll have a high degree of confidence as to whether CO2 storage is going to be viable at gigascale. Now I'm going to focus on the challenges and the options for making liquid fuels. And the options are not just climate change, but they're also high oil prices and also oil supply insecurity issues. And these additional issues here complicate the picture for doing carbon capture and storage and mitigating climate change for liquid fuels production, as I will show. What are the alternative options for reducing greenhouse gas emissions? Well, there's been a lot of attention given to the hydrogen economy, and I spent 15 years of my life thinking about the hydrogen economy, and I have thrown in the towel in this. I think it's best a long-term option, and in the discussion I can go into some of the reasons why I think that is true. But more recently, because the shine has sort of worn off the hydrogen option in many parts of the world, there's been a lot of attention to biofuels. And the biofuels that have gotten the most attention are sugarcane ethanol, grain ethanol, mainly corn ethanol in the United States, and cellulosic ethanol. Sugarcane ethanol is a very attractive option. It's competitive at oil prices of the order of $30 a barrel. You get deep reductions in greenhouse gas emissions with this, but it's an attractive option only for tropical regions with adequate rainfall. And so it's not in itself a universal solution, and this goes back to Stefano's point that there are no silver bullets for the dealing with climate change challenge. There are what I call silver buckshot, but not silver bullets in dealing with this. And sugarcane ethanol is one promising bit of silver buckshot. The second option is grain ethanol. The problem with grain ethanol, which is the focus of attention in the United States, this provides only marginal carbon mitigation benefits, and there are very adverse impacts on food prices, as we all know. The longer-term option is cellulosic ethanol, which is good for carbon mitigation, but this option is evolving only very slowly, and much slowly than we thought 10 years ago. And then in Europe, there's an intense interest in biodiesel, but as in the case of grain ethanol, this technology is based on food biomass with adverse impacts on food prices. In the United States and in China, and also more recently in India, there's intense interest because of the oil price and oil supply insecurity issues in coal-to-liquids technology. And this is very interesting because it's commercially proven based on coal gasification plus Fischer-Tropsch synthesis technology. It is cost competitive at oil prices of $55 to $60 a barrel. It's characterized by ultra-low air pollutant emissions at CTL plants and very low pollutant-emitting synthetic liquid fuels, mainly synthetic diesel, and you can also make synthetic gasoline in this way. And these Fischer-Tropsch liquids can be used in existing transport fuel infrastructures. That's a big advantage over both hydrogen and ethanol. But, and this is a really big but here, Fischer-Tropsch liquids are not helpful in mitigating climate change. If you make Fischer-Tropsch liquids from coal and you vent the CO2 co-product, the total fuel cycle-wide greenhouse gas emissions associated with liquid fuels production in use is about twice the rate for crude oil projects that are derived with crude oil-derived projects when you vent the CO2. And if you capture the CO2 and store it underground in geological formations, you can't do any better than reduce the fuel cycle-wide greenhouse gas emission rate to the rate for crude oil-derived products. So I want to now focus on biomass and think first and say something first about the urgency of shifting from food biomass, which is what we're using today, to lignocellulosic biomass. And it's important to observe that if you look at most of the estimates that have been made of prospective biomass supplies, mostly they are lignocellulosic biomass, and most of the lignocellulosic supplies are based on crop residues, forest residues, and municipal solid waste. And some is also due to potential dedicated energy crops, but these dedicated energy crops in the form of short rotation woody crops, switchgrass, mixed prairie grasses, for example, can be grown not just on cropland but also on marginal lands that are not used for food production, and so you have a tremendous potential for reducing dramatically or even eliminating the potential for competition with food production. As I said before, you can make a transition to lignocellulosic biomass if you can bring cellulosic ethanol into the market, but that transition is turning out to be much slower than we thought even 10 years ago. An alternative, potentially much faster route to lignocellulosic biomass would be to make synthetic diesel and gasoline by means of gasification plus Fischer-Tropsch synthesis. And a key aspect of this approach is that this route to liquid fuels can piggyback on the Fischer-Tropsch liquids that people want to make from coal, because the technology is already fully commercial for making Fischer-Tropsch liquids from coal. The drawback of doing this is there's not much experience with making Fischer-Tropsch liquids from biomass, because in biomass energy R&D programs around the world, almost all of the attention has been given to biochemical conversion, and there's very little attention given to thermochemical conversion based on gasification. So the approach, the key enabling technology for this strategy for any kind of carbonaceous feedstock is oxygen-blown gasification to convert the primary feedstock in by means of reaction with partial oxidation and steam is to make synthesis gas, which then can be shifted, as we've already heard, to the ratio that you need for making synthetic fuels, and this gives rise to a very low cost CO2 capture and storage compared to other approaches for making for energy conversion. And it's also a key to making clean liquid fuels and electricity out of these various carbonaceous feedstocks. And if you want to make liquid fuels, what you do is you react the two elements of synthesis gas, where you adjust the hydrogen to carbon monoxide ratio to the ratio you need for making synthetic fuels. You react them in the presence of an appropriate catalyst, and you can make methanol, you can make dimethyl ether, or you can make Fischer-Tropsch liquids, and there are other things you could make if you wanted to in this way. So it's sort of a designer approach to fuels production, and I'm going to focus here on Fischer-Tropsch liquids because that is commercial technology that the market is most interested in today. Now, if you're going to make Fischer-Tropsch liquids from biomass, the different approaches you can pursue are, first of all, to make biomass to liquids, BTL, with CO2 vented, and you can also do it with CO2 stored. And it's important to note that when you make a Fischer-Tropsch liquids from any carbonaceous feedstock, about half of the carbon in the feedstock ends up as a relatively pure stream of CO2. If you're not worried about carbon capture and storage, you just vent that to the atmosphere. But what it means if you are concerned about climate change, the capture cost for this is very low. It's essentially the cost of drying and compressing the CO2 to perhaps 150 bar for transport, so it's suitable for transport to the storage site and disposal in appropriate underground media. And the capture cost here is quite low. It's of the order of $7 a ton of CO2, because all you have to do really is dry and compress. And if you were to do this for biomass, it would transform the status of biomass from being carbon neutral, as it is for conventional biofuels, to becoming carbon negative, because you're storing photosynthetic CO2 underground along with the CO2 that you're storing photosynthetic CO2 underground, and this leads to an expanded role for biomass in carbon mitigation because of these negative emissions. It's important to note that coal has no significant future unless CO2 capture and storage works at gigascale. And if it works for coal, it should also be considered for biomass because of this negative emissions benefit and the fact that biomass is a scarce resource. So you want to get the biggest bang for the buck out of the biomass resources that you have. But I'm going to suggest that if you're going to pursue this option seriously, you ought to think about it primarily in the context of not standalone biomass facilities, but rather in facilities that co-process coal and biomass with carbon capture and storage, what I call a CBTL option with carbon capture and storage, because in addition to the benefits for BTL plants with carbon capture and storage, this enables you to exploit the scale economies of coal energy conversion, the fact that the average feedstock cost for these plants would be much less than for BTL plants, just because coal is inherently much cheaper than biomass. And, of course, it gives you an opportunity to exploit coal for making liquid fuels in a climate-friendly manner, which is not possible without adding the biomass to the system. And from the point of view of the biomass producers, this is interesting because much less biomass is needed to realize zero net greenhouse gas emissions than with conventional biofuels, and you would get higher market prices for biomass provider than he could get with conventional biofuels. So from this point on, I'm going to focus primarily on CBTL with CCS technologies. Here are three different options for gasification to make Fischer-Tropsch liquids or Fischer-Tropsch liquids plus electricity. The first one is co-gasification of coal and biomass in the same gasifier. The second one is gasification of coal and biomass in separate gasifiers that are parallel to one another. And the third option is biomass and coal gasifiers that operate in series. I think that in the long run, there's going to be the dominant technologies are going to be the first and the third in this series here. But I'm going to show you some results of our research for the second option here, which is two parallel gasifiers. And I'm going to focus on not just making liquid fuels, but on making liquid fuels plus electricity in so-called polygeneration plants that pass the synthesis gas once through the Fischer-Tropsch reactor and convert all the and use the unconverted synthesis gas for making co-product electricity. And one way to do that is this way, with these parallel gasifiers in a system that for which we had a design that would store about 90% of the carbon in the feedstock underground as CO2, and use the hydrogen that you derive from this biomass to compensate for the low hydrogen content of the coal-derived synthesis gas. This system here is a variant of that last one that has two different kinds of photosynthetic CO2 storage. In the first one, the only form of photosynthetic CO2 storage was the CO2 that is derived from the shifted synthesis gas that is produced after gasification of biomass. In this case, there's some additional photosynthetic CO2 storage associated with the particular choice of feedstock, which is mixed prairie grasses that would be grown on carbon-depleted soils. And the basic idea here is to exploit the potential for storing significant amount of carbon in carbon-depleted soils by shifting them these production lands to the growing of mixed prairie grasses. And this idea is based on some pioneering work that was done by David Tillman and his collaborators at the University of Minnesota in an article that received a lot of attention. It was published in Science magazine at the end of the year 2006. And the basic ideas that they found from experiments that they've been conducting in the northern Great Plains since the early 1990s is that sustainable grass yields increase monotonically with the number of species. The soil root carbon buildup associated with these mixed prairie grasses also increases monotonically with the number of species. The soil carbon buildup continues for a century or more. And the number that I'm going to focus on in the economic analysis that I'm going to show you in a few moments is their measured rate of carbon storage for a system with 16 species of mixed prairie grasses, in which they found that over a 30-year period, which is comparable to the period over which a conversion facility might operate, the average rate of carbon stored in soil and roots is about 0.6 tons of carbon per ton of carbon in the harvested biomass. And I also want to point out a very important ecological benefit of this strategy, and that is the potential for local biodiversity gain, in sharp contrast to concerns about net biodiversity loss that are associated with the growing of energy crops in the form of monocultures. So the analysis that I'm now going to show you is based on polygeneration plants that make both liquid fuels in the amount of about 18,000 barrels per day, plus a co-product electricity in the amount of about 450 megawatts of co-product electricity. These are based on these Fischer-Tropsch synthesis plants with once-through reactors. We looked at three different configurations here. One is a coal-only plant with carbon CO2 vented, a coal-only plant with carbon capture and storage, and then a third one that we looked at is a coal plus mixed prairie grass fuel plant with carbon capture and storage using just enough mixed prairie grasses to reduce the net greenhouse gas emissions fuel cycle wide for the Fischer-Tropsch liquids to zero. Because the basic idea here is we want to know how much co-firing do you need in order to get deep reductions in greenhouse gas emissions. And we're thinking about mine-mouth plant siting of these plants in southern Illinois. And as I said, I'm going to assume this $100 a ton carbon price here for the market value of CO2 emissions. And I'm going to focus on the economics from the point of view of farmers who might grow these mixed prairie grasses as an alternative to growing corn on exactly the same land. Okay, and by the way, I don't know if I mentioned $100 a ton of carbon price is equivalent to 8 cents a liter gasoline. And I'm going to show you that this strategy looks interesting at that, very interesting economically at that price. These are the greenhouse gas emission rates on the top here for gasoline and diesel fuels derived from crude oil. These are measured in kilograms of carbon equivalent per gigajoule of liquid fuel. The third option shown here is for one of these polygeneration plants that makes coal to liquids with CO2 vented. You see the greenhouse gas emission rate goes up about 80% relative to the crude oil-derived products. The fourth option here is a CTL plant with carbon capture and storage, and you can see that the greenhouse gas emission rate is reduced almost to the level of what it is for crude oil-derived gasoline and diesel fuel. The bottom option here with zero net greenhouse gas emissions is for this CBTL with carbon capture and storage plant, and you can see the amount of biomass that's needed to get net zero greenhouse gas emissions for these polygeneration systems is about 1/5 biomass and 4/5 coal. That's a key finding of this. Now, it might turn out that you get no credit whatsoever for soil and root carbon buildup in these systems. And if that turns out to be the case, it's no longer a zero greenhouse gas emitting plant, but you still get like a 65% reduction in greenhouse gas emissions relative to a coal-only plant with carbon capture and storage, which is shown by the penultimate bar on this particular graph. And this particular graph, which was generated by Julia Fioresi here, it shows the net flows of carbon for this system into the atmosphere and out of the atmosphere, and balancing those two flows to give you the net zero greenhouse gas emissions. I'm not going to focus on that, but you can study that at your leisure in the handout if you're interested in that. And I'm going to go and say a little bit about the design of this particular plant, which is located in the middle of that circle in southern Illinois there. That's in corn country. It's at a mine mouth coal plant. And for this particular plant that makes 18,000 barrels per day of synthetic liquid fuels plus 450 megawatts of electricity, requires about 1 million dry tons of mixed prairie grasses per year. And our estimate is that for that particular region, the mixed prairie grass yield would be about 10 dry tons per hectare per year. So that's about 100,000 hectares that are required for this system. And the average transport distance to the conversion facility would be 25 to 30 miles for transporting the biomass to the conversion facility. And we, with the help of researchers at the Illinois State Geological Survey, we identified a nearby very promising storage site in the Mount Simon aquifer. So this would we considered storing the CO2 in a deep saline formation near this plant. And then, as I say, what we wanted to do in this analysis is estimate the value of the strategy to the farmer. And we started off by considering first a coal Fischer-Tropsch liquid plant with carbon capture and storage at this $100 a ton carbon price. And we said, what are the prices that you could sell profitably this both the liquid fuels and the co-product electricity into the market at that carbon price. And then we also determined what the break-even crude oil price is. Okay? And then we said, well, that's not really the plant that we want to build. We want to build instead a plant based on coal and mixed prairie grasses, but we want to sell the liquid fuels and the electricity at exactly the same prices, so that the profit to the synfuel producer would be the same between these two alternative plants. And that condition determines the willingness to pay of the synfuel producer for the biomass at the plant gate. Okay? And it turns out that under these conditions, the willingness to pay for the biomass is about 4.5 times the price of coal. Okay? That's an extraordinary result that arises only because of this high price on carbon. Okay? If you didn't have the high price on CO2 emissions, you wouldn't get that. Of course, the farmer doesn't get that 4.5 times the coal price, and that turns out to be just shy of $100 a dry ton of the biomass. Okay? So it's a very high price. But he gets a price that's $55 to $60 a ton, which is about 2.7 times the coal price. That's what he gets paid, and at this yield of about 10 dry tons per hectare per year, his income is about the same as what he now gets from growing corn. But the difference between these two situations is there's a big government subsidy for growing the corn, and there's no subsidy at all in this particular system. What there is a price on CO2 emissions. Okay, and that's the incentive instead of a subsidy here. So it might turn out that you don't get that much credit for the soil and root carbon buildup. And if that were the case, if you had zero credit for soil and root carbon buildup, then the income to the farmer would fall by a factor of 2. Okay, and so it's not as profitable as growing corn on these lands at the present time. But that doesn't mean that this wouldn't be attractive without carbon capture and storage. It just wouldn't be attractive as an alternative to growing subsidized corn on existing croplands. But there are lots of other options for biomass, for example, using various residues for making liquid fuels that are likely to be attractive even with zero credit for the soil and root carbon buildup. A key aspect of this overall strategy is that the amount of biomass that is required to make a unit of liquid fuel is far less than for any conventional biofuel strategy. What I show on this particular graph, the 3 bars on the right-hand side are first generation, second generation, and third generation ethanol, cellulosic ethanol technology based on research being carried out at the National Renewable Energy Laboratory in the United States. And on the left-hand side, I show how much biomass is needed with, on the far left, the CBTL option with carbon capture and storage. And in this case, it's slightly different than the one I showed you before, because in this case, the plant makes only electricity, and it's not the polygeneration plant that makes this 450 megawatts of coal-fired or 450 megawatts of co-product electricity. It's just a recycle plant. And you can see that the amount of biomass needed to make 1 gigajoule of liquid fuel is about a half of a gigajoule of biomass input. And of course, if you don't get any credit for soil and root carbon buildup, you have to use a lot more biomass. But still, it's only about 0.9 gigajoules of biomass you needed to make 1 gigajoule of zero net greenhouse gas emitting liquid fuel. Okay, I want to stress that these options here require much less biomass input, and the reason for that, as you can see from this, is that the rest of the fuel input is coal. Okay, so much of the feedstock for these systems comes from the coal, more than half of the total, even with zero soil and root carbon buildup. So what is the status of these technologies? First of all, coal gasification technology is commercial. Fischer-Tropsch liquids technology is commercial. CO2 capture technologies are commercially ready for gasification energy systems. Not quite yet for the other systems, but for gasification systems, they're quite ready. One particular CO2 storage technology is fully commercial, and that's CO2 enhanced oil recovery technology, as we've already heard. And CO2 storage in deep saline formations is ready for mega-scale projects at the present time. And the consensus in the storage community is that in order to understand if CO2 storage is going to be viable at gigascale, billions of tons of CO2 per year, we need to carry out over the next decade, as quickly as possible, something like 10 to 12 megascale projects in alternative geologies, primarily deep saline formations, in order to understand this, and there's a real urgency in doing that. And coincidentally, the CTL and CBTL projects are very good candidates for providing the CO2 because of the very low capture cost with these plants. It's of the order of $7 a ton of CO2. So you can think of a bootstrap strategy whereby these plants could provide CO2 for some of these megascale storage demonstration plants while they're being launched in the market. The only element in this whole system that is not commercially ready is biomass gasification at large scale that would be required for, say that parallel gasification system. That technology could be become commercial by 2015 because we've already done pilot gasification facilities for small plants that operate at scales of the order of a few tens of megawatts of gasifying biomass. But at the same time, we can actually get started with CBTL much more quickly than that because the co-gasification option that I mentioned on one of my early slides here is commercially ready. And in fact, it has been demonstrated at Buggenum in the Netherlands, where a coal IGCC plant has been fired routinely with biomass to the extent of 30% by weight since early 2006. And in the United States, there's a Bard Energy CBTL project that's in the planning stages. It's a 50,000 barrel per day CBTL plant that is being planned for construction on the Ohio River, and startup date is scheduled to be 2011, 2012 in that time frame. And they're using exactly the same gasifier that's being used at Buggenum, and they have plans to co-fire with up to 30% biomass on a weight basis, and they're also planning to do carbon capture and storage either by means of enhanced oil recovery or storage in a nearby saline aquifer. And this project also looks quite real compared to all the other CTL plants that are on the board in the United States, on the drawing board on the United States. To finish up, I would like to present you three variants of this sustainable mobility project scenario to the year 2050 to explore the potential of this strategy in mitigating climate change. And the first thought experiment that I want to show you some results for is to keep transportation energy demand for 2050 at the same level as in the sustainable mobility project scenario, and to consider hypothetically, but totally unrealistically, that we would back out 100% of oil in transportation at that time, and choose a mix of CBTL with CCS technology and BTL with CO2 vented technology such that 100% of prospective biomass supplies in 2015 are consumed. And I'm going to assume for the CBTL system that 0.9 times that the biomass required is 0.9 times the CBTL energy use rate, and that's because I'm not going to assume any soil and root carbon storage in that. And then for the biomass required for the BTL system with CO2 vented, I am taking an estimate of how much biomass is needed for that particular system, and it's about 2.3 times as much energy is contained in the BTL liquids that are produced with that system. And the second thought experiment is to keep the transportation energy demand at the same level as in the first one, and the same mix of CBTL and BTL technology as in thought experiment number one, but I'm going to be much less ambitious in how much I do in this scenario. I just want to conform to the wedges strategy of stable emissions by 2050 at the same rate as today instead of getting rid of all oil. And the third option I want to do is say we shouldn't try to solve this problem on the supply side only, but we should also go after improved energy efficiency. And for this, I'm going to take the estimate of how much better you could do relative to business as usual according to the Tech Plus strategy of the International Energy Agency's Energy Technology Perspective 2006 report, Scenarios and Strategies to 2050. And they estimated that you could reduce demand by about 23% with their Tech Plus scenario. And this includes a doubling of the fuel economy of light-duty vehicles in this time frame. And again, I'm going to pursue the wedges strategy here and assume the same CBTL-BTL ratio as in thought experiment 1 and 2. For the prospective biomass supplies, I assume the results of a recent OECD study, biofuels is the cure worse than the disease. And what's interesting about this particular study is that the estimate of biomass is quite consistent with most of the other big assessments that have been done of the prospective biomass supplies. But I want to point out to you the numbers on the top of this bar here in light blue are for energy crops, dedicated energy crops, and the assumption made there was that the average yield would be 10 dry tons per hectare per year over 440 million hectares. That's a lot of land. It's about half the land area of the United States, but it is what is regarded as feasible in the judgment of most people who have looked at this. And these are the results of this exercise here. What I show, excuse me. Does this point here? How do I point with this? Okay, this one. Okay. This is the Sustainable Mobility Project demand projection as before, and this is the 100% oil backout thought experiment. And you can see for that system, the greenhouse gas emission rate in 2050 would be down an order of magnitude relative to what it is under the business as usual. And these two over here are the two wedges strategies. This is with constant demand, and this is with improved energy services over here. What I show at the bottom here is the total CO2 storage rate that is required for CBTL. It's the yellow bars on the top here, and down below is what is likely to be required for coal-fired power generation in this period, as estimated in the MIT Future of Coal study that came out in early 2007. I want to point out to you, for this scenario up here, you can still see there's a lot of oil being used in 2050, but it's slightly less than the amount of oil that is used today. And the rest of the fuel comes from the CBTL and BTL as shown here. And the other thing that I want to call your attention to is the total amount of cumulative storage of CO2 for these three scenarios, about 1,500 gigatons here, about 1,000 gigatons here, and about 900 gigatons here. And as I said, we don't know with a high degree of confidence how much we're going to have to do, but according to the IPCC special report on carbon capture and storage that came out in 2005, the consensus judgment was that worldwide it is likely that there's at least about 2,000 gigatons of CO2 geological storage capacity. And this is the amount of biomass that's needed for these different options here. You can see for the oil backout, the top of this bar is exactly at the level of this bar over here. That's by design, using up all the prospective biomass supplies. But I want to, and this shows that there's prospectively enough biomass to completely solve the transportation problem by reducing, by an order of magnitude, the greenhouse gas emissions to about 0.4 gigatons per year by mid-century. But we're not going to do that by 2050 because we're going to be using a lot of oil in that time period. And so what you really want to think about is one of these other options over here. And if you pursue the option, the wedge option here, one of these wedge options here, and especially if you pursue the energy efficient option here, you can see that the total amount of biomass required for that is less than the total prospective availability of residues, which means you can achieve a wedge stabilization strategy potentially, at least in principle, without even getting into dedicated energy crops, which is a very important conclusion. And at the end of the day, there are no significant technological hurdles to this strategy. There are no significant economic hurdles to this strategy. It is contingent upon the gigascale viability of CO2 storage, number one. And it's also dependent on these four characters being able to work together to make it happen. And those four characters have historically never worked together collaboratively. So it's a big challenge, institutionally and culturally.
Grazie mille. Allora io darei senza indugio il via alla discussione per i